the area about the chromatic number of digraphs. And what I'd like to get with this talk is to convince you that this is the chromatic number to consider if you consider chromatic number of digraphs. There are many ways to introduce it, and this is just one of them, but what I believe this is the right one. So let me start with the definition. So I will be using a capital D for a digraph. That's a directed graph. And if you see a G or H, that will always be undirected graph. So just have this in mind. So D is a digraph always. So no loops, as you wouldn't like loops when you color the things. But you allow two vertices to be adjacent in two directions. So an edge from X to Y plus an edge from Y to X could coexist at the same time. And then you define a coloring with K colors, a K coloring of such a digraph by requesting that every vertex is mapped into one of the colors. Let this be just integers 1 up to K. And then you ask that in comparison, for usual colorings of undirected graphs, you require that the color classes are independent sets. So no edge joins two vertices of the same color. And here you require that each color class is acyclic. So there is no cycle colored whose all vertices would be colored with the same color I. So that's the definition. And for the chromatic number, you want the minimum K such that such a thing exists. So now if you start with a graph, with an undirected graph, and then replace every edge by two oppositely oriented edges, then you see that in this definition, no two adjacent vertices should have the same color, because that would be a cycle of length 2. So, and this just means that if you do this, then the chromatic number of this digraph, doubly oriented undirected graph, will be the same as the chromatic number in the usual sense for undirected graphs. So this is a natural generalization. Another thing to mention is if you would like to see how large chromatic number of a digraph is, this is easy to recognize if a chromatic number is at most 1. You just need to show that there are no directed cycles, and that's an easy task to do. Now, for usual colorings, also two coloring is easy, and then if you want to have 3 or more colors, that becomes NP-hard problem from the computational point of view. And here, it is the case that actually even two coloring becomes difficult. So I'm not going to show you how it's done, but it's easy to prove such a statement. Now, just for an example, let me consider this digraph here. So it has 6 vertices, and it's almost 3 regular. So every vertex has 3 incoming edges and 3 outgoing edges, except you see it's not exactly 3. Here it's only 2 outgoing. Now let me add another vertex, and then from this vertex I join to all other vertices in such a way that I make it 3 regular. So here I'm missing 1 outgoing edges. It goes to this additional 7th vertex. And here I'm missing 1 incoming edge, so I'm coming into this one. So, and then you see you get what you would call a 3 regular graph, because every vertex has out degree and in degree equal to 3. This graph, it may have a 2 coloring, like the portion without the new vertex, it's 2 colorable, as you can see with here. So there is no cycle of the same color. But if you add the new vertex, you cannot color it with color 3. Of course, you can with colors 1 or 2, because you will get a cycle. So, for instance, here, new vertex back, you get a cycle. If you color it 1, if you color it 2, you get another one, and so on. And actually, you can see that however you try to true color this part, you get something which is similar than this one. So this way you get, this is actually a tournament, so on 7 vertices. So this is the tournament on 7 vertices with the 7th vertex. So everybody is adjacent to everybody, so, right? There is another interesting example. You take the Fano plane. So Fano plane has, in the usual representation, it will have 7 points. And another line. And then for each of the lines, you put a directed triangle on it. And so you do for each of these 7 lines in this Fano plane. You have 2 choices how to do it. So you get 2 non-isomorphic graphs in this way. And actually, they are both tournaments on 7 vertices then. So it's every 2 points are on the same line, so there is an edge between them. So it's but it's not this one, because this one doesn't have the same properties. So for instance, here every edge, every arc is in precisely 1 triangle, right? Because that follows from the definition of the finite geometry. But there are edges on 2 triangles. And interestingly enough, this one requires 3 colors too. So it's, yeah. Yes.
You're going to have a triangle made up of 3 edges from 3 different lines?
This one, and this one.
No.
They go to 3.
Edges that make a triangle are 3 different.
Oh, I see. This one, and this one. You're saying, yeah, right? Oh, maybe you're right. So, okay. So. That's a thought. So, yeah, I know it's different. Yeah, it's. But you're right. The argument wasn't correct. So, and this one is also not too colorable. So that's also an interesting exercise. So if you get lost later on, you can try that if you want. So now I said this is the chromatic number of a digraph, and why would it be the chromatic number and not just one of the possible ways? Because you can also say, I forget about the directions of the edges, and then I do the usual colorings, and people have considered such things too. So there are few slides or stories that I will tell you. So story 1 will be the one where I started introducing this number. Story 2, story 3, 4, and 5. So this is roughly the outline where I'm going during this talk. So let me start with the first thing, so with the circular chromatic number. So for any graph, undirected graph, you can define a circular chromatic number in the following way. So what you want, you look at the vertices of the graph, and then you map the vertices onto the points of a circle. And let's say that this circle has circumference r. So you could have r points at distance 1, for instance. Let's say 6. You could have r points at distance 1, but also other points there are in there. And you can map the vertices onto any point, and all you require is that if you map the vertex v here, and you map the vertex, let's say this is where you map the vertex u, you require that the distance between v and u is at least 1. So that says that the colors are different. So now, about 10 years ago, or a little bit more, I realized that this you can you can generalize this to weighted graphs. So if you have edges which have weights, you can say that the distance is at least the weight of the edge from V to U. Right? And in this case, you get a sensible notion of the chromatic number, or in this case, it would be circular chromatic number of a graph with weighted edges. Now, here you want to minimize this circumference. The minimum possible would correspond to minimum possible number of colors. So, and another thing which you can realize is that these weights need not be symmetric. So you will also require that this distance here around is at least the weight of from U to V. So the weights need not be symmetric. So once you do that, then you can naturally come digraphs. Because for a digraph, you can think like the edge is only in one direction, in the positive direction. So you require this be at least 1 for an edge. And you don't have any requirement for if there is no edge in a different direction. So you can mimic that putting an epsilon, a small epsilon weight on the other direction, and then you take limit as epsilon goes to 0. And you get the notion of a chromatic number of digraph. And it turns out it is exactly the same one as I introduced before. So it's the same one. Because if you put if you have an edge from V to U, this is of weight 1, and then the edge going the other direction is just imaginary. You just think a tiny epsilon weight. So basically it says that there is almost no restriction. And then if you have an acyclic subset, you can always, acyclic subset, which could be a color class in my first definition, you can always take a topological ordering of that acyclic subset so that all edges put forward. And then you can, sorry, I will do the backward. So all edges put backward. And then you can put the vertices of the same color in this order, one after another, because the edges in the positive direction will have the huge distance, and in this other direction, you don't care. It's just this tiny epsilon. When epsilon goes to 0, you can map all of them to the same point. So that's how you get to the notion very in a natural way. So this was this was where I've met this for the first time. And it was only a couple of years later I realized that actually the same notion was introduced in the 80s by Victor Neumann-Lara. So Neumann Lara was a founder of a graph theory school in Mexico. So he's dead now, but he was the father of graph theory in Mexico. So, and he introduced in 1982. He had the first paper called the dichromatic number of graph, and subsequently a number of papers in this area. So. I mentioned that I worked. So there is a story which I heard from my student Ararat, whom I asked to work in this area, and Ararat said, "Oh yeah, I heard the following story that Neumann Lara was at a conference, and so one day he was thinking about this chromatic number of digraphs, and one day he realized, oh yeah, now I understand this notion really well. So I understand things which he was searching about. And then the next day he died. So this was an unlucky thing. And so whenever I say to Ararat, let's try to understand it, he says, no, understand. So that's, but anyway, so people have looked at this before, and let me now switch to story number 2, Wilf Theorem. Wilf found this interesting enough result an upper bound on the chromatic number in terms of the maximum eigenvalue of a graph. So this looks like a Brooks theorem. If you would have a delta here, the maximum degree, this would be the easy part of the Brooks theorem. And there is the well, let's say the less trivial part of the Brooks theorem also goes with Wilf theorem. So actually, if there is equality, then you get one of the graphs from the Brooks theorem. It's a complete graph or an odd cycle. So lambda 1 of G is the maximum eigenvalue. So let me do this here. So lambda 1 of G is the maximum eigenvalue of the adjacency matrix of the graph. And it's interesting that this eigenvalue is playing the role. So it's always smaller than delta, than the maximum degree. And so it is an improved Brooks bound in some sense. Yes. Now, a couple of years ago, I discovered that this Wilf theorem works for digraphs. So it's, if you see, I've repeated the Wilf theorem above. So it doesn't seem difficult to prove. You just change G to D, and here you are. So, and actually, it is not so difficult to prove. So, but it works for digraphs as well. Now, when you work for digraphs, it's a little bit strange. Because my first thought was the following. Look at this. So if I have a digraph with the adjacency matrix, so the adjacency matrix always has zeros on the diagonal, and then just take a matrix which has many ones here in this part, and then all zeros here. Now this matrix has all eigenvalues 0, so the largest one is also 0. That's something suspicious, right? So I mean, how could a 0 be how could a 0 be the upper bound? Of course, you see in this case the graph is acyclic, so it is really chromatic number 1, and it meets the bound here. So that's a pretty good reason to believe that this is the right chromatic number, right? Okay, so let me continue. So Brooks theorem is weaker than the, but here is the version of Brooks theorem. I have to prove Brooks theorem for digraphs too. And it has the same flavor that there is the trivial part, and the equality can happen. So this +1 may be necessary, but only in specific cases. So, and here are two classes. So if you have an odd cycle and you have bidirected, so you replace basically the construction I mentioned at the beginning. You replace every edge by two oppositely directed arcs. Then you get a graph which does have the chromatic number, so equal to. So it's not. I didn't define what delta would be for a digraph. So what is the maximum degree? But you look at the let's say maximum in degree or maximum out degree or something like that. I will be more specific a little bit later. But let's just say that this is important to understand. So if you have a vertex which has 3 edges out and 3 edges in, this degree is not 6 but 3, right? Okay, so that's I just have to. I will clarify this delta a little bit later. So, but this is the Brooks theorem. Except there is one more class of graphs which are exceptional. So it's not only odd cycles and complete graphs, but it's also just any cycles. And so this works for chromatic number 3. So this will have chromatic number 3. complete graph has degree, let's say, k minus 1 and chromatic number k. And here it's just a cycle has chromatic number 2, any length, say 4, and degree 1. So, sorry, this is chromatic number 2, yeah, and degree 1. So that's, and these are all the cases that occur. Now, when you consider critical graphs for coloring, Galai's theorem is the first notion which occurs. So Galai proved a theorem about structure in critical graphs. So critical means if you remove any vertex, then the chromatic number goes down. And in such graphs, he would consider, in such a graph, you cannot have vertices of degree less than, so if the chromatic number is k, degree could be at least k minus 1. Because otherwise it wouldn't be critical, right? You could remove the vertex, color the rest, and then you could put the color on this one. And Galai was interested in what is the structure on these small degree vertices. There could be vertices of degree k minus 1, but what is the structure? And his result basically is that the vertices of small degree induce a subgraph which has the following structure called Galai tree today. It is composed of complete graphs or odd cycles, so could be a cycle of length 5. Could be like that. In this way. So every block looks like this. So this is the essence of Galai's theorem, and it naturally works with list colorings. You can think of having the rest of the graph, big vertices, you can color them with k colors. And then, since the graph is critical, each of these vertices is left with this vertex is left with 3 colors. Sorry, you color with k minus 1 colors, with fewer number of colors than chromatic number. So you're left with the same number of colors, here 3, here 2, here you have degree 5 colors and so on. But they are different, so it's like a list coloring version, right? And here is a definition what we mean by list coloring, that each vertex has a list of, let's say, 5 colors, maybe 1, 5, 2, 1, 5, 2, 7, 10. So these 5 different colors that you can use to color this vertex, and then you need the usual coloring. And Galai's theorem says that every block of this low degree subgraph is one of these Brooks graphs that comes from Brooks theorem. And the same occurs for digraphs. So if you have digraphs, each block looks like a cycle or a W-oriented cycle. So let me put W-oriented this way. Or a W-oriented clique and so on. So that's the and moreover, you can say how the colors look like on these classes. So the setting is that you just say I have such a graph where each vertex has the number of available colors is equal to the degree, and then you show if this graph is not colorable, then it must have this special structure of Galai's theorem. And it is amazing that this works. This extends to digraphs. So here I'd like to point out that this is the first time I've specified this degree. So it's a little bit unusual. So I say that I take the maximum of the out degree and in degree of each vertex. So the number for the degree of the vertex. And then delta would be like the maximum of this over all vertices. Why do we need to take a maximum? So why wouldn't you take maybe a minimum of these two quantities? Because you see, the following is definitely true. If you have a digraph and it's critical, so a critical digraph for, so let's say K critical. So it has chromatic number K, but if you remove any vertex, chromatic number goes down. It's K minus 1. So if I have a vertex which has at most K minus 2 out neighbors, then I can color the rest by removing this, by using criticality on this. And then you see, maybe it has many in neighbors, maybe many edges come in, but it only has K minus 2 out neighbors. Well, so I color the rest, well, including these vertices, and then on the out neighbors, at most K minus 2 colors appear. So I color with K minus 1 colors. I would like to get a contradiction. And then I can use a color which doesn't occur on the out neighbors. And this won't give me a cycle, right? Because there wasn't cycle before. Now, if it would be a cycle through this new vertex, it must leave the vertex with the same color. So, but I've chosen a color which doesn't occur on the out neighbors. So it seems that more natural thing would be to replace this maximum with the minimum. So that's, but the unfortunate truth is that it doesn't work anymore. So if you replace it, here is a counterexample. So you look at this digraph, and the lists are as shown. So this vertex has out degree 1, so it has only one color. And you see, and so on for the rest. And you see that this graph is not colorable with these lists. So these two vertices at the bottom have no choice. This one cannot be 1 because you would have a triangle. So the upper one, and then you get a 2-2 cycle for the other two. So this would be a counterexample, but maybe that's a little bit special. So, and one thing that this came as a surprise. So, is that actually it doesn't work. Because if you go with the minimum, the problem becomes hard. So not only that it doesn't work always, but it's even impossible to say when it works. So if you just consider digraphs and you put at list coloring at each vertex, you put the number of colors equal to the minimum of the in degree and out degree, and ask if this is least colorable with these lists. This is a hard problem. This is NP complete. Okay, any questions so far?
It is always colorable with one more.
Of course, yeah. Of course, yeah. It's trivial by that argument that I've showed, yeah. So if you put a +1 here, whenever this is different or so, then it works again here. Now, here is a funny thing. So this is an improvement. So I'll explain the things, but just forget about the +1 and forget about this hat. So this thing basically says that there is a Brooks theorem result so that you can color every digraph with at most alpha times delta colors, where alpha is strictly smaller than 1. Now this is a little bit suspicious because it's for usual graphs it won't work. Now, but it does work if you have some restriction on. Oh, and also here, I forgot to mention. So here you need an additional condition. D is connected, that you don't have cycles of length 2. You don't have digons, because if you have digons, this is the same as looking for the chromatic number of usual graphs. So the theorem here says that there is a constant strictly smaller than 1, so that every digraph of maximum degree delta can be colored with alpha at most less than alpha times delta colors. Now, here, this is a kind of definition what you use for the delta. Instead of one thought would be to take. We know we cannot use the minimum of the two things of the out degree and in degree. So one other thing would be to use the average. But even better, we can do the geometric mean, so which is a better, a smaller, which gives a smaller value. So this is interesting enough if a thing is regular when you have a normal definition of the maximum degree, and then this is actually the result, which is showing. And the only condition is you don't have a digons. Now this was this result was actually an outcome or a weaker outcome of a conjecture that we've made. So Kim and Johansson proved for the usual chromatic number of undirected graphs that if you have a girth at least 4, so if you have a triangle-free graph, then the chromatic number, then there is a Brooks theorem of improved version of the Brooks theorem. So instead of delta, which is the upper bound for in the Brooks theorem, you get delta over log delta, which is much better for large delta. And actually, for digraphs, this conjecture that I've made with Colin McDermott back when I started working on this shows that for digraphs we just say digirth 3. So we don't just forbid digons. And then we would have something. So instead of this, we've proved alpha times delta, where alpha is smaller than 1, but it's still far to get it. So we've tried the usual attack on the Kim's and Johansson's proof for the girth, but so far we couldn't make it work. So it's that's the ultimate conjecture I'd like to come to, but it's I don't know if how hard it would be. So now one could ask if this could be maybe even improved. So but no, even if you require girth much more, you can require girth 100. Then still you can't get any better than delta over log delta. So there was a result by Bolobash. I think it was Bolobash proving this, that for every given girth, the Bolobash result is for undirected graphs, and every degree delta, there exists an undirected graph G, which has large girth, so bigger than G, and which has delta at most, the maximum degree at most, this given delta, and the chromatic number bigger than delta over log delta, up to some constant, which is, I don't know, this is like 1 over 20 or something, is constant. And the same thing works actually for digraphs. Now, yeah, I wanted to give some proofs. I could go into proof of this. This is a probabilistic proof, so let me mention how one would prove this. It's not too far from Bolobash's proof. So what you do is you just take so you want to show that there exists a digraph D with girth. So this is not only saying that there are no small undirected cycles, but even in the underlying graph you have no cycles. Okay, so this is not digirth, this is girth. And the maximum degree of D is at most is delta, and the high chromatic number. So, and constant delta over log delta. So it's a normal thing you do in probabilistic proofs. You take a random graph. And there are arbitrarily large such graphs. So it's you take a random graph on n vertices. N is large. Now here I need a digraph. So I'll fix a probability P. I think 2 times k squared over n, I think would work. So this is a probability for an edge to be included in this digraph. And then, so if it happens that my coin decided that there will be the edge between the 2 vertices I'm looking at now, I choose probability 1/2 to direct it that way and 1/2 to direct it this way. So then this 1/2 will disappear. So it will say with probability P over 2, this edge is directed in existent, is directed in that direction. Okay. So I'll flip the coin, I mean the biased coin for each edge, and I make a random graph with these probabilities. And it is standard to show that these graphs wouldn't have too many short cycles, so you can remove few vertices or few edges and get large girth. That's a standard thing to do. And then also that these graphs will have large chromatic number. It's unlikely that there will be a big set. So I can get the numbers just to get impression how this works. Yeah, so you would like to take a big set which would be what's the chromatic number? Yeah, so would like to show that the alpha of D is small, where alpha of D is the largest. That would correspond to the largest independent set in the usual sense, so the largest acyclic set. So this is the largest size of the largest acyclic subset, and that this is small. So this is appropriate, is small. So how you do that? Well, you see, if you have let me just say that I want to prove this is smaller than some constant. So basically, if it happens, I take a set of vertices where this will be independent set. So this will be acyclic. Now I have so let's say cardinality is S or S plus 1. So let's put this is strictly smaller. Let's say cardinality of A is S. I have S factorial ways to label the vertices in left-right order, and for one of them, for at least one of them, all edges will be forward. Well, some of them are missing, but all the existing edges will be forward. And you see, it is when I got this edge, it was only probability 1/2 that I have selected forward. So that it's a very small probability that I have such an edge. So you count how many edges you expect in this set, and then you count what is the probability that all of them will be forward. And this is much smaller than even if you count all choices. So you have n choose S choices for taking this set and S factorial for reentering this. And this probability is so small that you don't hope for having that. So that's the usual thing to do. Okay, so that's here I come to I will touch a little bit the tournaments. This is a special area by itself. One thing is that if you have a tournament is a complete graph, and then you orient the edges in some way. So it's a complete directed graph, oriented graph. Here I claim that the chromatic number of the tournament is actually, if I go a little bit back, let me just go a little bit back. You see this conjecture. The conjecture says that the chromatic number would be like delta over log delta, and actually for tournaments it is true because of this this bound. So this is delta is at most the number of vertices in the tournament on n vertices. So and this is delta over log delta times a constant. How do you prove that? That's also an easy exercise. So you show that every tournament contains an acyclic subset. Tournament on n vertices contains an acyclic subset of size log n. Now this is actually very easy. So you just start with any vertex, take any vertex, v. Now v has some out neighbors and some in neighbors, and let's say it has. So these are the out neighbors, these are the in neighbors. So let's say this is a little bit. So these are the out neighbors, these are the in neighbors. Let's say this is a little bit bigger. Then I will concentrate on here. So I delete this, and I keep this vertex, and I concentrate on here. So this is n over 2 vertices. I find, this is just by induction or by the same procedure, I find log 2 n over 2 vertices which make an acyclic set, and then I add this one. I don't get any cycle, right? Because everybody's directed into that vertex. And this is just log 2n minus 1. So altogether I have log 2n vertices. So I have such a big set which I can use to color with a single color, right? So this is a big set. So I do that, and now I take another one. So after, you see, so each time I color log n vertices. So I win, yeah, right? Well, the only thing is that n is getting smaller when I'm coloring, so I don't get really log n, but I get log n prime, whatever this smaller n prime is. But you can still do it. So basically, because you can actually do this procedure up to, as long as you have n over log n times log n vertices left. So then the logarithm is essentially the same. The logarithm of this number is essentially log n. And once I have fewer, then I can just use a color for each remaining vertex. So that will be all hidden in this little O of 1. That all hides in there. So that's an upper bound. Now it is interesting that this upper bound is close to the truth. Actually, you have tournaments. Some of them require very few colors, right? If you have a transitive tournament, you can color it with one color because it has no cycles. So there are some, but if you take a random tournament, then it needs many colors. So that's been well known for a while. So actually, what it turns out, about half of the upper bound. So, and again, the proof of this is probabilistic from the first principles of probabilistic methods. So you just take a random tournament. Again, you choose probability p equals 1/2, and then you orient each edge one or the other way with equal probability, and you ask what is the probability that you have a large acyclic subset, and large being about twice this logarithm. So, and then it turns out that the probability. So you take this random orientation. So random orientation of edges, and then you take a subset A, which has size, let's say L, and let L be 2 times logarithm plus 1, let's say. So this 2 times logarithm, this 2 comes 2 times logarithm will occur there. And then you show that the probability that such an A exists, probability that A is acyclic, that there exists an acyclic A of size L is tiny, so it's little o of 1. So that's, again, yeah, I have a minute, so I can do this. So just how can you prove that? So probability that there exists an acyclic set, this is clearly, at most you guess what this subset would be. You have n choose L possibilities to get this subset. And then the probability that this is acyclic, again, you take L factorial orderings of the vertices, and one of them needs to have all edges forward. So this is times the probability that all edges forward. So, and this probability, you have L choose 2 edges, and each of them points forward with probability 1/2. So this is 2 to the minus L. L choose 2. And then you need to deal with the factorials and Stirling formula and so on, and you prove that this is going to 0. If n is large, this is tiny. Okay, so that's the usual way of proving such things, and it works like butter here. Now another issue, it's that the chromatic number of tournaments is related to really some central conjectures in chromatic number theory. Let me just mention how. But I believe that Paul may speak a little bit more details about this topic, so I won't go into the topic. So, but let me just mention co-chromatic number. This is a notion that some people have looked, and it's you color the vertices of the graph so that each color class is either independent set or a clique. So it's that's a little bit different notion, and I can explain very briefly how this is related to the tournament. So let's take a undirected graph. Okay, I will do it undirected graph on 4 vertices. Let's say is this one. And then I assign a tournament to this graph as follows. So first of all, I need the numbering. So I number vertices 1 up to n. And then I decide, I look at a pair of vertices, 1, 2. If there is an edge, I put a forward arc. So I put an arc forward, and I put an arc forward. And if there was no edge, I put a backward arc, right? So I put a backward arc here. Backward arc here. Oops, this one wasn't. This one was there. There is this one. So 2, 4, 6, right? Yeah. So it's so from a graph, I get to a tournament, and if I have orientation, I can go from a tournament to a graph, right? I take all forward edges will give me a graph. Now, look at this. So if you happen to have a coloring of this graph, and let's look at the, well, it's not a big graph, but let's try to imagine this. Suppose I have a set of 10 vertices, no edge between them. So in this tournament, how will they look like? They will look like a backward tournament, right? So you can, this is an acyclic subdigraph, so you can use one color. So if you have an independent set, you can use in the tournament, you can use one color. Now if you have a clique in this graph, then this will be a forward oriented transitive tournament. So a clique, so any any independent set and any complete subgraph in G determine a transitive subtournament of T, one or the other direction. So you see that there is a relation, because each color class here will be a transitive subtournament. So, but there is involved a definition of you need to order the vertices. Now, Paul, will you speak about the Erdős-Hajnal at all, or? So I'll skip this. There are and the equivalence with this Allon-Pach conjecture. Yeah, okay. So I'll skip that. Now I'll cover one more result maybe. So it's just showing that that the chromatic number is a global parameter. So that's this is an interesting fact that you cannot determine what the chromatic number is if you know local picture. So if you from each vertex you know how the graph looks like in certain neighborhood, you cannot tell what the chromatic number is. It's a global parameter. And so this is usually determined by this result of the Gerth that I mentioned. But here is a much better one. Is this one is this is a graph for graphs, not for digraphs. So for graphs, it says the following. So for every chromatic number at least 4, it didn't say for every k at least 3, I guess. Here in my theorem is at least 3. So k at least 4. So if you have chromatic number at least 4, and then you take a graph with there exists graphs with chromatic number at least 4. Let's say 1000, chromatic number 1000, in which if you take any large subset of vertices, it's so let's say k equals 1000, then any large subset of vertices is tricolorable. So there is this epsilon which you see in my theorem here, but it says large subset means at least epsilon, at most epsilon n. So large, well, sorry, any small, any not too large, but could be linearly large in n. So let's say the epsilon is 1/1%. So every subset of 1% vertices is tricolorable. And this shows that basically we can't say determine the chromatic number. If you look at the 1% of the vertices, you can't say anything, right? And the same holds for digraphs, except you go one step lower. For digraphs, you have chromatic number at least 3. So I forgot to say 3 here, I guess. Yeah, maybe it should be. Let me explain the result for usual graphs, right? Okay. So I take graphs in the projective plane. Sorry, k. No, k. It's okay. K is okay. Yeah, this should be 3. This is 3 colorable. So, but let me describe why the 3 coloring is interesting. So, I can there are graphs in the projective plane which look like quadrangulations. So here locally they would be even 2 colorable. So, but the chromatic number is 4. So chromatic number is 4, right? I of g is 4. Now, if you take in this graph, it's not true that because you can take such a cycle will need 3 colors. So this cycle will generally have at most about square root n. So if you have n vertices, this will have about square root n vertices, and it will need 3 colors because it's an odd cycle. So that shows that here this 3 colorable cannot be improved to 2 colorable, because you have graphs which are 4 chromatic. They are huge, so they have n vertices, and then there will be subsets of size square root of n which would need 3 colors. So you cannot. But for digraphs, you can do it. You can go 1 color down. So. So here the construction of these graphs is probabilistic again, and I would maybe only make a comment why these 2 doesn't go down to 1. So I'd like to make a comment why this cannot be shown that this is 1. You see, having this 1, this would say that you have a graph of large chromatic number, k. Think of k of something large, and then so this epsilon depends on k, but there is some fixed epsilon, and then n is n could be very large. So then a fixed portion of vertices would always be just 1 colorable. 1 colorable means there is no cycle in there. But you can always take a cycle, directed cycle. So it would say that in this graph you will have a directed cycle. Every directed cycle will have at least epsilon n vertices. If this would be true with 2 replaced by 1. So I'd like to show that this cannot be done. So the question is, are there? So k and epsilon are fixed now, and then asking, are there arbitrarily large digraphs of chromatic number at least 3 such that every directed cycle has length at least epsilon n is large. Now here I do need chromatic number at least 3, because if you only go for 2, you can make the following construction. You can just take a long graph which goes, so there are vertices, but they all edges go in the direction around. So if you make this, you see that every cycle must go all the way around, so it is long, right? It is long proportionally to the number of vertices. So, but these graphs would be 2 colorable, because you can just color one of these, let's say 2 vertices with 1 color and all the rest with another color, or 1 segment with 1 color and the rest with another. So here you need k is at least 3, and this I forgot in the theorem. So now, but if k is at least 3, this cannot happen. So why is this true? Why is this true? Now I will recall a theorem of Reed, Seymour, there was Robertson, and Thomas. They proved that in a digraph, they proved the version of Erdős-Pozsony's theorem for digraphs. In a digraph, V on n vertices, there are 2 outcomes. Either T disjoint cycles. So either there are T vertex disjoint cycles, or a set A of size at most f of t. So this is some exponential, or well, it's maybe a little bit more than exponential function of t, vertices covering all cycles, all directed cycles. So this is true for every digraph. Now, if I would have such a digraph, I know the chromatic number is at least 3. So if I remove this set A, and I get no cycles, it means that this set A contains a cycle, right? Because if it doesn't, the remaining set I can use color 1, and for this set I can use color 2, so it would be 2 colorable. But I'm assuming that the chromatic number is at least 3. So this shows that the condition that every cycle has this length, this shows that cardinality of A is at least epsilon, has size at least epsilon times n, right? And on the other hand, the graph doesn't have too many disjoint cycles, because if you have many disjoint cycles, so one of them will be shorter than epsilon n, right? If you have more than 1 over epsilon such cycles, then but on the other hand, t is at most 1 over epsilon. And then this just gets a contradiction, right? So every digraph, if it is large enough, either t is at most 1 over epsilon, or this f of t. So t is at most 1 over epsilon, or things prepared, but I'm already over my time, so it's I wanted to say a few words about planar things, but now I'm even out of time for the questions, I guess. Thank you.